If you would recall, we've been talking about complex roots of numbers, and we related this to zeros of a polynomial, x-intercepts of a polynomial, solutions to polynomial equations. All these things are related. Let's see another example of that. One that works out a little bit better than a friggin' x to the fifth. I don't know why I was thinking fifth roots would be okay. It's 360 divided by 5, it's 72. So I went with 6 roots because 360 divided by 6 is 60 degrees. Those will land on angles that we recognize. So let's think about finding the 6 complex sixth roots of 64. What to the 6th power is equal to 64? This is the same thing as finding the complex solutions to the equation x to the 6th equals 64, because that's the same question. What to the 6th power is equal to 64? The real ones are pretty easy to find. The inverse of a 6th power is a 1/6 power. So I can just undo the 6th power with a 6th root or a 1/6 power. When we undo an even root, we have to remember that even exponents do not respect negatives. They make all the negatives positive. So we got to put a plus or minus. Even exponents is that friend that's always like, oh, just cheer up. Michael, that's not how it works. That's how neither sadness nor depression works. You don't just turn it off. That's what even exponent does. Take that negative and make it positive. Erase some information in the process. So we just got to remember, when we undo an even exponent, we've got to tack on the plus or minus, because the negative gets raised to an even power and becomes positive. The real ones are easy to find. We just do a 6th root plus or minus, and we get plus or minus 2. That's why I went all the way up to 64. 2 to the 6th power is 64, and also negative 2 to the 6th power is 64. But we know there are 4 more, because it's a 6. We're trying to find 6 roots. There have to be 6 of them, 6 complex ones. We're going to do this in 2 styles. First is algebra style. First, we're going to use algebra style. That's going to be factoring and the zero property and completing the square. Traditional. So I start with my equation. X to the 6th equals 64. I want to use the zero property, so I get everything on one side. I make one side equal to 0. We need a 0 for the zero property. Now I have x to the 6th minus 64 equals 0. I'm going to start off with my factoring process. My factoring, I started off with the difference of squares. So factoring part 1 was the difference of squares. X cubed minus 8, x cubed plus 8. This is just a variation on x squared minus 64. But instead of x minus 8, x plus 8, I have x cubed minus 8, x cubed plus 8. So we open with the difference of squares. This factors into 2 cubics, a difference of cubes and a sum of cubes. So we remember our difference of cubes and our sum of cubes power. If we don't, the important thing is not to remember specifically what it is, but it's important to remember that such a thing exists, so that you can go, oh, I don't know what it's called. It's the sum of cubes, but I can't quite remember what it says. So along comes Google and says, oh, I'll help you remember that stuff. We never have to not know for very long, but we have to know what we're looking for. That's why Google's working so hard on that thing where it identifies a song just because you hum it to it. Otherwise, it's like, oh, you know that song that's like, oh, da da ba 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 da ba ba. You're like, oh, I have no idea what you're saying. Because your friend, it's always your friend that can't carry a tune that's trying to say, you know that song done by that guy. It was sometime between 10 and 20 years ago. So you remember, right? How am I supposed to remember that? He performed it on that show, you know, with that one other guy. Anyway, Part 2 is I'm going to factor the difference and the sum of cubes. So the x cubed minus 8, that's those first two, x minus 2, x squared, 2x, 4. And the sum of cubes, x plus 2, x squared minus 2x plus 4. Now I've got it all factored as far as I can go. I don't have any factors of 4 that I can make a 2 with or a negative 2 with. So I'm going to have to deal with those separately. But look at the first two, the linear factors. X minus 2. Here's an x minus 2. Here's an x plus 2. In the zero property, those give us the two real ones, the two real zeros we already knew about, plus and minus 2. What's left over are those two quadratics, each of which will give us two complex zeros. And now everything is as expected. We knew there were two real zeros. There are the two linear factors that led to our real zeros. And quadratic factors will give us complex zeros. Irreducible quadratic factors will give us complex zeros. So there's the 2 and the negative 2, the two real ones we already knew about. But now we got to solve those two quadratic equations. We could use the quadratic formula if we want to be like all those Brittany and Justin wannabes. Or we can complete the square. Like actual math people. We can show some class and complete the square. So that's going to require that we remember how completing the square works. If you're going to rely on the quadratic formula, you're completing the square anyway. You just don't want to know how things work. And you're going to be one of the parents that complains, why couldn't you just do it the old way? It's not like they remember the old way anyway. So I don't know what they're complaining about. It's just like, move, parents, get out the way. Let your kids struggle. Anyway, the completing the square part happens in the x squared and the x term. I take half of a 2 and square it. Half of 2 is 1, 1 squared is 1. I need a plus 1 to complete the square. So I'm going to take that plus 4 that I have, and I'm going to pull off a plus 1. That leaves behind plus 3. Now I have x squared plus 2x plus 1. Those first three terms, by design, will factor as a square, x plus 1 squared. That was by design. We picked the 1 to make that square happen. Now I can just do inverse operations in reverse order. Subtract 3 from both sides. Take a square root. Remember, when we're undoing an even exponent, we have to do plus or minus. Because even exponents don't respect negatives. So we got to attach our plus and minus. And finally, we could just subtract, add 1, subtract a negative 1. Subtract a negative 1. And simplify the radical. The square root of a negative makes an I in front of the radical. So here are our two of our complex zeros. Negative 1 plus I times the square root of 3, and negative 1 minus I times the square root of 3. We would have to do the same thing on x squared minus 2x plus 4, but the only difference is instead of plus 2, we have a minus 2. So the only difference is that this x plus 1 will be an x minus 1. So instead of subtracting a negative 1 from both sides, oh, it is subtract 1. I couldn't remember which one I added, which one I started with. And it's too blurry for me to read. So we do subtract 1. The only difference is now have x minus 1 equals plus or minus the square root of negative 3. So I will add 1 to both sides. So I'll get 1 plus or minus I times the square root of 3. Any questions? There are the 6 complex zeros, or sorry, the 6 complex roots of 64. 2 and -2, -1 plus or minus I times the square root of 3, and 1 plus or minus I times the square root of 3. Any questions? It only seems like it's a lot to remember because it's a lot to remember, and you have to remember all of it all the time in perfect detail. And if you're wondering, if you're worried, like, oh, dude, are we going to have to do this on a final exam or a quiz or a test or something? Not without backup. Any questions? Comment? Yes. Plus or minus makes 2. So it's a -1 plus I root 3 and -1 minus I root 3. 1 plus I root 3 and 1 minus I root 3. We just get lazy and put the plus or minus symbol. But it's okay to be lazy and put the plus or minus symbol, because if we have a polynomial with real coefficients, any complex zeros will always come in conjugate pairs, A plus or minus BI. Complex zeros of polynomials with real coefficients always come in conjugate pairs. Any other questions? How's everybody okay? Everybody's, I can read all your minds. It's like, ugh, why did I come to class today? I can tell because you're looking like this. I've learned to identify what students look like with masks on, so you can't hide it. It's all in the eyes. Trigonometry style. Important thing to keep in mind that we're going to solve the problem that we just solved. Coming up with the answer is not the point. There's another way to solve the problem, so we should learn that way too. It's about balance. You can't just have one style all the time. You've got to have a balance. Cobra Kai taught us that, right? The Cobra Kai series, that taught us. You have to have balance between the different styles. So we should also use trigonometry style. It's okay to prefer one, but you have to be proficient in both and anything else that shows up. There's also graphing calculator style. So we have there's some information that we have already. If we have x to the 6th equals 64, we already know that we get plus or minus the 6th root of 64, which is plus or minus 2. Before we switched to algebra style, we already had the real zero. This is just the first step, arithmetic style, form 1. Can't remember what form 1 is called. No, I don't remember my lightsaber forms. So we had the plus and minus 2, the real ones from before. So I'm going to plot those in the complex plane, 2 plus 0i and 2 minus 0i. Since we're looking for sixth roots, we know that they're going to be 360 over 6, 60 degrees apart. The sixth roots will be 60 degrees apart. So I'm going to draw a circle of radius 2, and my complex zeros will be 60 degrees apart. So there's one at 60 degrees. "60 degrees later will be at 120 degrees. "60 degrees after that will be at 180 degrees. 60 degrees after that will be at 240 degrees. And 60 degrees after that be at 300 degrees. And then just to complete the circle, so I got my two real zeros, 2 plus 0i and negative 2 plus 0i. Then my complex zeros, we can see them happening in conjugate pairs. Here are the two at 1 plus the square root of 3 and 1 minus the square root of 3i. And then over on the other side, we've got negative 1 plus the square root of 3i, negative 1 minus the square root of 3i. These points are on a circle of radius 2. So this one's at 60 degrees. So the coordinates here are 2 times the cosine of 60 and 2 times the sine of 60. Cosine of 60 is a half. Sine of 60 is root 3 over 2. So if I multiply by 2, this point will be at 1 and root 3. That one down there in the fourth quadrant will be the conjugate of 1 and square root of 3. That's 1 and minus square root of 3. Has the same x coordinate and opposite y coordinate. Or same real coordinate and opposite imaginary coordinate. Over on the other, in quadrant 2, on the other side, in quadrants 2 and quadrants 3, There's -1 minus I root 3 and -1 plus I times the square root of 3. We ended up with 60-degree reference angles going all the way around. That's why I picked 6 roots in the first place. Any questions? Since we're in a math class, or since we're solving equations, we would want to know if we're right. And this is not a problem that I got from a book, so we can't look back in the back of the book and check the answers to the odd numbers problems. But when we're solving equations, since we're solving equations, we can always check our solutions to see if they work. And this is the part where like, oh man, you want to check our solutions for 6 roots? We have to raise things to the 6th power. Which isn't a lot of fun, but all we'd have to do is take each of these and plug them into the equation. So we're trying to say what the solutions to x to the 6th equals 64 are. It's easy to check too. That one works out. It's easy to check -2. It's going to be a little messy to check 1 plus or minus 1 plus or minus I squared of 3. So this is going to be not fun, which is why I'm not going to do that. But we just have to take 1 plus I root 3 and make 6 copies of it. It's going to be a bunch of FOIL. The advantage is we've got I squared is equal to -1. So every time an I squared pops up, it just becomes a -1. So if we just take these first two, we do 1 plus an I root 3 plus another I root 3 plus I squared times square root of 3 squared, which is 3. So I have 2I times the square root of 3 plus 3I squared. Square root of 3 times the square root of 3 is the 3. I times I is I squared. But the advantage that we have is that I squared is equal to -1. So I have 1 plus 2I root 3 minus 3. And 1 minus 3 is -2. And that's those first two. Now I just multiply this by yikes. Now it becomes a game of strategy. Notice that there's 4 copies of 1 plus I root 3. I know what the product of 2 of them is. So I'll just replace these with -2 plus 2I root 3. And I'll replace this one with -2 plus 2I root 3. So now it's just a matter of strategy. Don't just start and go from left to right. because PEMDAS said, go from left to right. Go from left to right, unless there is some better way to do things. Any questions? How's everybody okay? If you want to do the plan ahead version of things, go ahead and multiply the -2 plus 2i root 3 times the 1 plus I root 3. And then then you'll know what 3 of them is. Then multiply that by 3 more. So that would be a more plan ahead version. I'll multiply it out real quick. I'm really fast at multiplication, but really only when I know what the answer is supposed to be. Any questions? Now I realize I could have busted out my calculator and said, well, I don't have my calculator to do this, but if I'm going to use technology to check my answers, I might as well just use technology to solve the problem in the first place. That's not what we're here about. Any questions? Comments? Snide remarks? How's everybody okay? This is a lot of algebra, and I didn't do these two problems. I didn't do the algebra style and the trigonometry style to try to sell one as being better than the other. It's just different. They're both different ways of accomplishing the same goal. So we should know both ways of accomplishing the same goal. If I tried just to sell one over the other and suppose that it is better because it's faster or easier or whatever. So you should do trigonometry style instead of algebra style. I am advocating that you not know something. And that's kind of like the opposite of what I'm supposed to be doing. We're here because we want to know stuff. That's right. I said we're here because we want to know stuff. This class is optional. You don't have to be here. So my assumption is you're here because you want to learn trigonometry. I'm not sure that that's true. Any questions? How's everybody okay? If you're not okay, it's week 14. And that means there's only week 15, 16, and 17 to go. So that's 6 plus 1 more this week, 7 more class meetings. You only have to meet 7 more times. And then pass, lose, or drop, you'll be done with trigonometry. And moving on to pre-calculus. But since this class comes before calculus, it's also a pre-calculus class. If anybody asks what class you're in, you say, well, I'm in pre-calculus. I don't know why algebra gets pre and calculus gets pre. Like, is algebra like pre-geometry? And it's not like you're done with algebra either. My favorite question is that everything is linear, right? Or not linear, but because trigonometric functions. Everything is a linear story. You're being railroaded. It's a linear story progression. You do arithmetic, you do algebra, take a little break, do some geometry, you do some more algebra, you do some trigonometry, you do some more algebra, then you do calculus, then you do calculus, then you do calculus. And so it raises the question, what comes after calculus? And my usual answer is Math. Math comes after calculus. All those stuff up through calculus, that's preparation for like math stuff. You know what I mean? Which kind of messed up because if you decide to be a math major, I know you all want to be math majors. You decide to be a math major as an undergrad when you haven't finished your calculus classes. You don't even know if you like it. My parents are, oh, my little kid in the 5th grade, they're good at math. Like, well, you have no way of knowing that. I usually don't say that out loud to parents who are proud of their kids' success in math. All right, that's going to do it for today. I will see you all on Thursday, and we'll talk about trigonometry endgame. Everybody have a good couple days. I'll see you on Thursday. Thanks for playing.